Hi everyone, welcome back. So we're going to continue looking at our series on factorization of polynomials by introducing this thing called the factor theorem, which gives you a way to actually find a factor of your overall polynomial. And we want to be able to do this because we're going to be dealing with cubic polynomials eventually, and we're going to want to graph them. Okay, now when you graph them, you want to find their x-intercepts. And the best way to do that, at least for a cubic polynomial, is to factorize it into at least a linear factor. Could be 3, could be 2. And use the null factor theorem or the null factor law to solve and find your x-intercepts. Okay, just like you can do the same thing for quadratics. You can factor it into 2 factors and then use the null factor law to work out the x-intercepts. You can, of course, for quadratics, use a quadratic formula. But there is a quadratic formula, there is a cubic formula, I guess you could call it, to find the x-intercepts for cubics, but it is really big and really tedious to do. Okay, so we're not going to introduce that. We're going to find our x-intercepts for cubics by factorizing them. But first we have to learn how to factorize them. Okay, so previously we've seen that if we perform a division and we get no remainder, then it must be that the divisor is a factor of the dividend. Okay, so if we use numbers, let's say I use 273 divided by 13, I get an answer of 21. That means that 13 is a factor of 273 because there's no remainder. It also means that 21 is a factor of 273 as well. If you want to use polynomials, we could use the polynomial x cubed. Let's do x cubed plus x squared minus 14x minus 24, and we could divide this by x plus 2, and you would get an answer of, if you did this whole long division process, you get x squared minus x minus 12 with no remainder. So that tells you that x plus 2 is a factor of this original polynomial on top. And of course it also tells you that this x squared minus x minus 12 is also a factor. Okay, when we say factor, in this video at least, we're talking about things that divide with no remainder. Okay, in general though, factors are just things that you sort of multiply together. Okay, all right, so that's what it means for you to be getting no remainder. It means that you get a factor of your dividend. So let's formalize that a little bit in terms of maths language. So if I use this linear polynomial, beta x plus alpha, for this to be a factor of some polynomial p of x, so if I divide it, then I need to have no remainder when I do that. So p of x divided by this linear polynomial must give you a remainder of 0. Okay? Is there a way to quickly check whether we get a remainder of 0 or not? If we don't want to go through the whole dividing process every time we want to check if it's a factor? Yes, there is. We can check it using the remainder theorem, which is what we did in the last video. Okay, let's state this factor theorem explicitly. So, factor theorem states that beta x plus alpha is a factor of p of x if and only if p of negative alpha over beta equals 0. That is, if p of x divided by beta x plus alpha has a remainder of 0. So this part here is talking about using the remainder theorem. Okay, substituting this negative alpha over beta, which comes from your linear polynomial that you're dividing by. If it turns out that you get an answer of 0, that tells you the remainder is 0. And now we know that if the remainder is 0, then your linear polynomial must be a factor of p of x. Okay, that's the factor theorem. If you use the remainder theorem and you get an answer of 0, then the linear polynomial that you used the values of in the remainder theorem must be a factor of your polynomial p. The problem with this is there are infinitely many values of alpha and beta for you to try and use. Okay, you want to find a factor. Okay, you want to find a factor. So what you want to do is be testing values of beta and alpha, that combination of negative alpha over beta. You want to test values, putting them into your polynomial and checking whether or not you get an answer of 0. If you do, then it turns out that the linear polynomial that you've used is a factor. But there are so many combinations of beta and alpha that you could use. Where do you even begin? Okay, we want some way to narrow down some values that we could try and use to first just work out whether or not it actually is a factor. Okay, so we just need to find some values of beta and alpha to put into our polynomial, to substitute into it, to find that special linear factor that gives us a remainder of 0. We can use a bit of a shortcut here. Okay, if p of x is a monic polynomial, and remember monic just means it's got a leading term coefficient of 1, so it could be x cubed plus 3x squared minus x plus 1. That's monic because this coefficient of x cubed is just 1. Okay, so whenever you have a monic polynomial that you wish to find a factor for, then beta is always going to be equal to 1. Because if we're trying to find a linear factor of this polynomial, okay, we want to factorize this into a linear factor times something else, okay? So our linear factor is going to be of the form beta x plus alpha times, some other business here to get this polynomial back. In fact, we know in advance that this linear factor here, this beta only has to be equal to 1. Because if I just make that equal to 1, then I know that this term here is just going to be x squared, and so when I do x times x squared, I get x cubed. Okay? If that's like 2x times x squared, then I'll end up getting 2x cubed, which is not what I want. So if my cubic polynomial is monic, I know in advance that beta is equal to 1. Okay? And so we only need to worry about finding values of alpha that we could use to determine what linear factor we have. Okay? Now, which values of alpha do we try and use to find this linear factor? Well, if you think about it, our linear factor is going to be of the form, if I write this out again, it's going to be x plus alpha times something, 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 something. Okay, and eventually at the end of this other thing that you've got here to multiply, you'll have some other number. Let's just call it k for now. Okay, if you do your whole expansion, multiply all of this out, you'll end up getting, somewhere at the end, you'll end up getting blah, 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 alpha times k. Okay, and when you equate coefficients, you know that this constant term must be equal to this constant term. Okay, and what that tells you is that you've got some number, alpha times some other number, to get positive 1 in this case. So the only values of alpha that you need to check are the factors of positive 1, which in this case are positive or negative 1. Okay, you could be negative 1 times negative 1, which would give you positive 1 for this constant factor, or you could be using positive 1 times positive 1, which would still give you this positive 1 factor here. Okay, so the values of alpha that you can check are factors of the constant term of your polynomial. Okay, let's see how we use this in practice. Okay, so find a linear factor for this polynomial and hence factorize it into linear factors. And the hint is, what values of alpha should we try? So we already know that beta is going to be 1. Our factor is going to be of the form x plus alpha. Okay? Because beta is 1, we know because this is a monic polynomial. The coefficient of x cubed is 1 here. So, how do we find a factor for this? Well, let's figure out what values of alpha we're going to try and use in our remainder theorem to determine whether the remainder is 0. So we're going to use alpha that has values of factors of this constant term. So alpha could be positive or negative 1, positive or negative 2, positive or negative 3, or positive or negative 6. Okay, each of these numbers is a factor of positive 6. So now we just start going through this list of values for alpha and substituting them into our polynomial. So let's start with alpha equal to 1. See what we get. So p of 1 gives us 1 cubed minus 4 times 1 squared plus 1 plus 6. 1 cubed is 1, 1 squared is 1, so 4 times that is 4. So 1 minus 4 is negative 3 plus 1 plus 6. Well, we know that's not equal to 0. Okay, so using an alpha value of 1, that's not, well, technically we're using alpha value of negative 1, but we're just substituting 1 into here. But that doesn't give us a value of 0 at the end. Okay, so we know that x minus 1 is not a factor. That's what we can gather from this information. Okay, because if we substitute alpha into here, or rather we substitute negative alpha into here, we get something other than 0. Let's try p of negative 1. So negative 1 cubed minus 4 times negative 1 squared minus 1 plus 6 equals, okay, negative 1 cubed is negative 1. Negative 1 squared is 1 times minus 4 is minus 4. So we've got negative 1 minus 4 is negative 5. Minus another 1 is negative 6 plus 6, you get 0. And that's what we want, okay? And what we can gather from this is that x plus 1 is a factor. Okay, so what we've done is we've used the remainder theorem to determine which factors of the form beta x plus alpha is a factor of this polynomial. And the fact that we've got a monic polynomial, that tells you that beta is going to be 1 for any of these linear factors. So we're only testing values of alpha. Okay, in the first one we tested an alpha value of negative 1. And remember, when you use the remainder theorem, you're using p of negative alpha over beta. So if alpha is negative 1, then we're going to be using negative of negative 1, which just turns into a 1 over here. Okay, if we've got x plus 1, if alpha is positive 1, then the thing we substitute into our polynomial is negative 1. And that's why I've put negative 1 here. Okay, but what we've determined is that x plus 1 is a factor. Now what we can do is use long division, if you'd like, to factorize this, because we know that we're not going to get any remainder, so this should just turn into x plus 1 times some quadratic. Okay, that's us factorizing this polynomial. And to determine this quadratic, we can use long division. So let's quickly do that. So we'll do x cubed minus 4x squared plus x plus 6. We're dividing this by, we're dividing this by x plus 1. We're dividing it by x plus 1 because I know that it's a factor. Okay, so let's do that. We get x squared up here. Going through the long division process, I'm going to just quickly go through it because you guys have seen plenty of examples by now. Okay, so you can just skip ahead and if you want, you can watch me do this, but really we're just trying to find the quadratic that we get at the end. So you can skip ahead, and once we find that quadratic, you can play the video again. Okay, so the quadratic that we get at the end is x squared minus 5x plus 6. So that means this polynomial can be factorized into the form x plus 1 times x squared minus 5x plus 6. Okay, and we know there's no remainders when we do that because we already used the remainder theorem to determine that when we use this factor here in our polynomial, we get an answer of 0 using the remainder theorem. Okay. Now what we can do is we can check, can we factorize this quadratic? can we continue the factorizing process? Well, we've partially factorized it at least. Maybe we can factorize this quadratic as well and produce 3 linear factors. Okay, so now we just go back to the process of factorizing quadratics. So one thing you can attempt to do is find 2 numbers that multiply to give positive 6, but add up to give you negative 5, and those would be the numbers that you use in your factors. And in fact, you can do that with negative 3 and negative 2. So we can factorize this quadratic into negative x minus 3 and x minus 2. Okay, so overall, this cubic polynomial can be factorized into 3 linear factors. The first factor we found by using the factor theorem. Okay, we tried some values for alpha, or rather negative alpha, in our polynomial that we used to find our remainder. And we found that if I substitute negative 1 into there, it gives us a remainder of 0. That tells us that x plus 1 is a factor of this polynomial. Then I can use this factor to divide my polynomial and find this quadratic. And that tells me that I can write my polynomial as x plus 1 times that quadratic that we found as an answer. Finally, you can then try and factorize this quadratic, which in this case we can. And what we've seen is that we can factorize this original polynomial into 3 linear factors, which, if you were trying to graph it, would correspond to 3 different x-intercepts, which you could solve. Let's do another example. So find a linear factor of this polynomial here, and hence factorize it. So first of all, what values of alpha should we try to use in our remainder theorem? Now remember, if it's a mnemonic polynomial, beta is going to be equal to 1, so we don't have to worry about beta. We're just finding alpha, which is the factors of 6. So alpha equals positive negative 1, positive negative 2, positive negative 3, positive and negative 6. So now we just try them. P of 1 gives you 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. We get 1 minus 2 minus 5 plus 6, and that does indeed give you 0. Cool, so what that tells us is that x minus 1 is a factor. Why does that keep happening? Okay, so x minus 1 is a factor. Cool, now what can we do? Well, we could go and use long division to factorize this polynomial into linear factor multiplied by a quadratic and try and find what that quadratic is. Let's do it another way though. Let's just continue using these values here to try and find some more linear factors. See what happens. So we've already done p of 1. What if we do p of negative 1? Just keep going down the list. So we get negative 1 cubed minus 2 times negative 1 squared minus 5 times negative 1 plus 6. And you can work that out, but it does not equal 0. Okay, so x plus 1, not a factor. Okay, try the next number, which is 2. So p of 2 equals 2 cubed minus 2 times 2 squared minus 5 times 2 plus 6. And again, you can go and work that out. It's not equal to 0. Okay, so that means x minus 2 is not a factor. What about the next one? Negative 2. P of negative 2 gives us negative 2 cubed minus 2 times negative 2 squared minus 5 times negative 2 plus 6. What does this equal? Well, you can work it out, and it does indeed equal 0. So that means that we found a factor, and the factor is x plus 2. Okay, so what that tells us is that we found p of x can be written in the form x minus 1 times x plus 2. And we also need a third factor so that we multiply all the x's together and we get x cubed. Okay, and this is also going to be a linear factor of some kind. And we know that that's going to be an x because we're going to have x times x gives us x cubed. And our job basically just is to find out what number goes here. And we could continue going through our list of numbers that we've got here until we find it, but we don't have to. Because if I expand all of this stuff out, I'll have -1 times +2 times this number at the end here. That should end up being the constant term of our polynomial. And the only number that fits, that's able to do that, is -3. Okay, so that also tells us that x minus 3 is a factor of this polynomial. All right. Cool. Now, in the last two examples, we've seen that we can factorize those particular cubics into 3 linear factors corresponding to 3 x-intercepts for a cubic graph. But that's not always the case. Okay, you won't be able to factorize it into 3 linear factors all the time. However, there will always be at least one linear factor if your cubic has nice integer coefficients. So you'll always be able to find a linear factor. In the next video, though, we'll see that it won't always be of the form x plus something or x minus something. It could be 2x plus something or 2x minus something, all right? But for now, we're just focusing on when that beta value is 1. So first of all, let's do this one. Find a linear factor of this polynomial, use division to factorize, and we'll see what we get, okay? So we need to figure out what values to put into our polynomial to find this remainder of 0. Beta again should be 1 because this is a monic polynomial, so we only have to care about alpha. And in this case, alpha will be the factors of the constant term, which could be +1 or -1 or +2 and -2. So let's try each of these one at a time. P of 1 gives you, well, I'm not going to work through this because this is just arithmetic, so I'll just cut to the chase. You end up with 3. Okay, so that's not right, so that means x minus 1 is not a factor. We could try P of -1, and you also end up with 3. So that means x plus 1 is not a factor. We could try P of 2. We end up getting something like 12. What is going on? 12. So again, that is not a factor. X minus 2, not a factor. And we could try P of -2, which is the only one remaining. And so yes, that one indeed gives us a remainder of 0. So finally we found that x plus 2 is a factor. Okay. Now, in fact, there's only one linear factor, and the reason for this is because there's only 4 possibilities of the alpha value that we could try to find that linear factor. If we could factorize it into 3 linear factors, then 3 of these possibilities should have given us an answer of 0. But the fact that only one of them has given us an answer of 0 tells us that only one of the factors is linear, which in this case is x plus 2. There are no other linear factors because there are no other possibilities that have given us 0. Okay, so that tells us that this is going to be a quadratic of some kind. It's going to be x squared plus something, x, plus, and we know that this number here at the end has to be 1, because if I do 2 times that number, I have to get this constant term here. Okay. You can use division. You can use long division to divide this polynomial by x plus 2 to find this quadratic. I'm actually not going to do that in this one. I'll just equate coefficients. Okay, so if I expand this out, I end up getting x cubed. I'll replace this question mark with a b. Okay, so I get x cubed plus bx squared plus x, and then I can do the 2, so 2x squared plus 2bx plus 2. Okay, now equating coefficients, what we see here is that we've got this x squared term. If I combine these two x squared terms here, I'll get b plus 2 times x squared plus a whole bunch of stuff. And we actually don't need to know anything else because we know that the coefficient of the x squared term is 1. So that tells us that b plus, far out. What is going on? B plus 2 equals 1. And so that tells us that b equals -1. Okay, so when we factorize this polynomial, it turns out that p of x can be written as the linear factor that we found before, x plus 2, times this new quadratic that we found, which we know that the fact that b is -1 and that it looks like this is going to be x squared minus x plus 1. And you can try and factorize that quadratic. I'm not going to be able to do it. Okay, first of all, you can check the discriminant of that. It's not going to give you anything, so there you go. Okay, so we can't factorize it into 3 linear factors, but you'll always be able to find at least 1. That was a heavy video. Okay, there was a lot of stuff going on in there, so take your time with it. Okay, go through all the examples again, make sure you understand what I'm doing. Okay, we're trying to find factors of polynomials, in particular cubics. Okay, and one way that we can do that is test some numbers using the remainder theorem. And if we end up getting a remainder of 0, we can use that along with the factor theorem to then translate that into a factor. Okay, so go back, review the video if you need to. Apologies for the length. It is a lot of stuff to take in, but we have to get through it. So hopefully you got through it okay. I will see you next time.